Yesterday, I discussed about a renormalization group study of quantum criticality and emergent phenomenon in fermionic system. In today's lecture, I will focus on quantum Monte Carlo studies of quantum criticality and emergent phenomenon in fermionic systems. I will study mainly sign problem-free quantum Monte Carlo study of such emergent phenomenon. Here's the outline of this lecture, today's lecture. First, I will give you some really brief introduction to quantum Monte Carlo and the fermion sign problem. Actually, this was already done by nicely by Simon yesterday in his lecture. After that, I will discuss in some detail about the Majorana representation, using Majorana representation to solve the fermion sign problem in quantum Monte Carlo simulation. And then I will discuss some symmetry classification of fermion sign problem using the Majorana representation. In the end, I will give you some examples of using sign problem-free quantum Monte Carlo to simulate a number of interesting quantum many-body systems and to discuss various quantum critical point. I will discuss three kinds of quantum critical point. The first is the H quantum critical point. The quantum criticality only occur at the boundary or edge of the system, but not in the bulk. The bulk is still gapped. The second quantum critical point I will discuss is the fermion-induced quantum critical point, namely the transition in usual non-dot sense is first order, but in such fermionic system, this transition can be induced to be continuous, to be second order. And also, probably some of you are familiar with this deconfined quantum critical point. So yesterday, Simon introduced the method of quantum Monte Carlo and how useful it is, and also the issues associated with the quantum Monte Carlo. The main issue which associated with quantum Monte Carlo is the sign problem. Okay. So for quantum many-body system, we have a quantum Hamiltonian. Such quantum Hamiltonian usually have a non-interacting term. Let's say for fermionic systems, which is the fermion bilinear for non-interacting part. It also have an interacting part. Normally, for a real material, it has interactions between electrons or fermions. Okay. And this, let's say this is operators. This H naught is a non-interacting part, which is some fermion bilinear. Okay. And here H is for spin 4 electrons is a 2n by 2n matrices. Okay. N is the number of sites. Okay. And to compute the physical property of such a system described by this quantum Hamiltonian, we usually compute the partition function associated with this Hamiltonian H, which is the trace of e to the minus beta H. Okay. As the Hilbert space of this quantum many-body Hamiltonian of the quantum system is exponentially large, doing the trace is exponentially hard. Okay, but we can using quantum Monte Carlo to do the trace. So we do this using Hubbard-Strzenovich transformation. Here is this HI is an interacting term, which is the 4 fermion interaction. So for interacting model, we don't know how to do the trace in some efficient way. Okay, so we need to convert this interaction into some fermion bilinear. As Simon nicely discussed yesterday, So we can do some sort of Hubbard-Stranovic transformation. And this trace of this e to the minus beta h after the Hubbard-Stranovic transformation can be converted to this form. This trace. It's kind of a path integral. So I neglect some intermediate step as that was discussed already yesterday. So we introduce some auxiliary field, and this auxiliary field depends on the lattice, the position of the lattice site or bound I, and also depends on the imaginary time. The trace here is time ordered. Okay, so this interacting problem is converted by Hubbard-Stranovic transformation to some non-interacting problem. But now this non-interacting problem coupled with the background or auxiliary field. And this auxiliary field depends on the lattice site and also imaginary time, or depends on the space-time in the imaginary time sense. Okay. And now, since this is a fermion bilinear, we denote this as H, which depends on the auxiliary field or background field. And then we can do the trace, since these are bilinears. And this trace, as Simon discussed, this trace is a determinant. Okay. So this identity matrix is 2n by 2n plus G. Okay. Again, here, this H is a 2n by 2n matrix. Okay, I probably, let's say this is H naught, the original non-interacting part. Okay, so this H is not a physical Hamiltonian. It's a fermion bilinear after the Hubbard-Stranovic transformation. So the form of this H depends on what kind of Hubbard-Stranovic transformation you do. Okay. So now, this, sorry, there's we still some of all possible background field configuration, auxiliary field configuration. Okay, and then we consider this as the Boltzmann weight for doing a Monte Carlo simulation. Okay, quantum Monte Carlo essentially is still a classical Monte Carlo method. So we just convert a quantum problem into some classical problem, and then do classical Monte Carlo simulation. And for classical Monte Carlo simulation, we really need a probability. And we can treat this, this Boltzmann weight as the probability if this is positive definite. But this might be positive or negative for a generical this 2n by 2n matrix H. Okay. Yeah, if you have any questions, you can stop me at any time. If this is bigger than 0, positive definite is sign free. Okay. If not, and then it's the sign problematic. Either positive and negative. Two cases. Problematic. And then we asked if, or on what kind of condition this Boltzmann weight or this determinant is positive definite. And if it's positive definite, we say that we can solve this kind of quantum Hamiltonian or quantum metabolic system numerically and exactly. Okay, because the computation time for solving this kind of sign problem-free model is only polynomial in system size and inverse temperature. Okay. If it's polynomial in system size and inverse temperature, we can always, by increasing number of computers, do parallel computation to solve such problem, to the accuracy, any accuracy we want. But unfortunately, for probably for many interesting quantum metabolic systems, the sign problem actually occur. For instance, the positive U Hubbard model away from half billion. Okay, that's the really interesting model. We would like to know whether it's superconducting at low temperature. Whether it supports high temperature superconductivity is still open question. But up to now, we still don't know how to solve the sign problem of such positive U Hubbard model away from half billion. It doesn't mean that it has sign problem. Maybe there's some way to solve the sign problem in this model in the future, since there is no proof that the positive U Hubbard model has sign problem away from half billion. There is no such proof. Okay. As Sam mentioned, sign problem depends on the basis, and maybe in the future some good basis can be found to solve that the sign problem.
Is there any case where there is a proof that there is a sign problem?
I'm sorry?
Is there any case where you can prove there is going to be a sign problem?
Yeah, I think this random bound IC model in 3D that has sign problem.
And you know there's no basis change that will help
you? No, yeah, I don't know the proof. Yeah, because this I think in the paper you mentioned yesterday by Choyo and Weiss. So the
for every model, if you go to the eigenbasis, you don't have a sign problem. But going to the eigenbasis is not an option.
Yeah.
Diagonalize the problem.
that may not be the only basis where there is no
Exactly.
sign.
And
Yeah.
So, and what is known to NP hard is that trying to find a basis, that step can be NP hard. Yeah, so the generic algorithm that will try to find a basis, but sometimes attempt to solve an NP hard problem, so that would be NP hard in itself. So finding generically a basis is not an option. But that doesn't mean that sometimes you might find one, or that you try to solve a problem entirely different, not by finding the right basis, but by doing something else.
Yeah.
So so there's no such statement as this sign problem is NP hard. A particular try to solving it.
So there's no proof.
no proof. Yeah. Yeah, I'm not sure for any quantum model there's any proof. Yeah, seems no
Something
proof.
like with the quantum Hall ground states.
Yeah,
I'd be very surprised if there's a way to do that with a sign problem.
You mean Cairo?
Yeah.
Uh-huh. Yeah. Yes.
Suppose I can choose a phi so that there's no sign problem, but this phi happens not to be the right Hubbard topology field. Then what happens?
not, I mean, you choose not the correct Laplace-General transformation?
It's not correct in the sense that it doesn't capture the physics, but it has no sample.
Yeah.
What happens in this case?
I mean, the problem you solve is not the problem you intend to solve, right? You solve another quantum problem, right? For instance, you can use some Hubbard-Stranovic field for attractive Hubbard model. And then the problem you solve is the physics of the attractive Hubbard model instead of positive Hubbard model. Is that the question you? Okay, we can discuss later. And fortunately, there are certain models which are sign problem free. A typical example of sign problem free model is attractive Hubbard model, which has this non-interacting part which describes the hopping of the fermions on the lattice, and this attractive view describes the interactions between spin-up electrons and spin-down electrons on a given site. Okay. And the way to solve the sign problem of this model is to choose Hubbard-Stranovic transformation such that this H here appears in this determinant can be written as here H can be non-Hermitian. It's not a real Hamiltonian. It's or we can call it Hubbard-Stranovic Hamiltonian. Okay. So this is this fermion binomial obtained after the Hubbard-Stranovic transformation. It can be either Hermitian or non-Hermitian. That's okay. For this attractive Hubbard model, we can choose some Hubbard-Stranovic transformation such that this H can be written as a sum of spin up part, okay, sorry, plus the spin down part. Moreover, this spin up part and spin down part, they are tiny Walser partner of each other. Okay, when we trace out the fermions, the Boltzmann weight we obtain for a given background field, auxiliary field, which is a product when they are decoupled, this Boltzmann weight is a product between spin up and spin down. Okay, when they form tiny Walser partners, this is positive definite because this the up part is a compressed conjugate of down part. Okay, such a Hubbard-Stranovic transformation, so this some tiny Walser can map this H up to H down. If this can be done, it's sign problem free. Okay, because the spin up weight is a compressed conjugate of spin down weight, such that the product of these two parts is positive definite. And then this model can be solved in polynomial time. Okay. And this is the usual way to solve the sign problem. Here we notice, so there is a condition using this kind of algorithm. First, this Hubbard-Stranovic transformation is decoupled in this way, which conserve particle number. Okay. So this binomial is a form of C dagger C, which conserves the particle number. Second, it has a spin up part and spin down part. Okay, there's some relation between two parts, or in general, we can have an even number of species to find some relation between this internal relation between these fermions such that we can prove it's sign problem free. So how about spinless fermion. Okay, so if we want to simulate a quantum many-body system which consists of spinless fermion instead of spin-4 fermion or SUN2 fermion, but or SU2n plus 1 fermions, SU3 fermions. Okay. And then for this situation, how to solve the sign problem? Is there any way to solve the sign problem? And this is the first question. The second question, how about interacting superconductors? Interact superconductors. Okay. For instance, the model has C dagger term. Okay, which describes the charge 2e. Sorry. Superconductivity, or even more exotic, the model can have C dagger, KL term. Okay, this is describes some charge for mean field description of charge for E superconductors. And this is this situation which the sign problem of such situation cannot be solved using a conventional algorithm or conventional method. Okay. So the idea to solve sign problem related to this kind of system is to use the Majorana representation. So, okay, so Majorana fermion is a real fermion. It really doesn't care about particle number conservation. Okay, so it's kind of a natural generalization of usual complex fermion algorithm. Okay, so this is a natural way to solve sign problem in interacting superconductors. Moreover, for each spinless fermion can be written as two-component Majorana fermion. So there's still some, in terms of Majorana fermion, there's some internal degrees freedom. Okay, in terms of complex fermion, spinless fermion is just species only. The flavor is n equal to 1. But in terms of Majorana fermion, it's a two-component Majorana fermion. Maybe we can use some internal relation between the two-component Majorana fermion to solve the sign problem related to the spinless fermion or SU2n plus 1 fermions. Yes?
This won't work for a repulsive univariate model?
Doesn't work for repulsive Hubbard model away from half-finite. So that problem is still open.
To understand why it doesn't work, because just saying that spinless fermion becomes doubled sounds like, okay, so you've got two spinless fermions up and down. Well, okay, they interact. So.
Yeah, they interact. Moreover, this kind of method doesn't solve all spinless fermions. There's still a requirement, condition to be sign problem free. Yeah. Okay, to be concrete, I discuss a specific model. For instance, if we look at a spinless fermion on the honeycomb lattice, the model which was discussed by Simon yesterday, and this model has free fermion hopping, spinless fermion hopping on the nearness label hopping on the nearness label bound, and also an interacting term, let's say nearness label interaction. So I write it this way: m minus 1/2 times nj minus 1/2, such that the system actually is at half-finite. So again, there's still some requirement to be sign problem free. Okay. And for this kind of Spinach fermion, so we can use Majorana fermion to represent complex fermions. For each complex fermion, we can introduce two component Majorana fermions. Okay, it's like a real and imagined part of the complex fermion. Okay, so now we have indices 1 and 2. So we call that Majorana indices, internal indices. Okay. And for this problem, this non-interacting part, we call it H naught. H naught, in terms of this Majorana basis, can be written. Sorry, this which nearest stable bound, we call it JK gamma G 1 plus I gamma. Okay. So you see that this component Majorana component 1 is separate from component 2 in the Majorana basis. So if you for the attached view Hubbard model, this non-interacting part, which the spin up and the spin down also separated. Okay. And for this interaction in terms of Majorana is let's say for a given bound JK, which I gamma J 1 gamma J. Sorry. 2 I gamma K1 gamma K2. Okay, this is a density operator in terms of Majorana, which is product between 1 and 2 at a given site. Okay, so this is the nearest stable bound. Let's check. And then we can switch between this and this, such that we move component 1 together and component 2 together. So this can be written as a minus sign here times the interaction I gamma J1 gamma K1 I gamma J2 gamma K2. Okay. So now you can imagine that this 1 indices like spin up, these 2 like spin down. And then we can do the usual Hubbard-Stranovic transformation like attractive view Hubbard model. Here is a minus sign here. Okay. So this after this Hubbard-Stranovic transformation, and this can be written as an auxiliary field. So now the auxiliary field depends on the bound indices instead of site indices. For the Hubbard model, attractive Hubbard model, the auxiliary field live on the site. So now auxiliary field live on the bound. Gamma J1 gamma. Okay, so after this Hubbard-Stranovic transformation, this 4 fermion interaction term is converted to fermion bilinear coupled with auxiliary field. Okay. So now we successfully separate component 1 and component 2. And this doesn't mean it's sign problem free. Okay. So then we want to integrate out Majorana fermions. Since 1 and 2 are separated, so we can separately integrate out Majorana component 1 and Majorana component 2. Okay, so we will get a product of 2 weight. And integrating out Majorana fermions is more complicated, is subtle than integrate out complex fermions. Integrate out Majorana fermion will give you a quantity which is the square root of a determinant instead of a determinant. Okay, So integrate out the complex fermions there, you will get a determinant. Okay, but if that C dagger C, instead of C dagger C, is gamma Majorana fermion transpose and gamma, you will get a square root of this determinant. And when we take the square root, we really don't know. There's a sign ambiguity first. Okay, and we really don't know whether the weight we obtain is positive or negative. However, if we can find some relation between component 1 and component 2, although we don't know, so when we integrate out the Majoranas, we will get a product of these two weight. And this W1, for the attractive view, is W up and W down. Here is W1 times W2. Okay. And we don't know what is W1 and what is W2, the sign. But if we find some relation between W1 and W2, and then we can say that it's sign problem free on some condition. And again, if we find a tiny Walser symmetry between component 1 and component 2, okay. In that case, if there's a tiny Walser symmetry, which so again the Hamiltonian obtained from Habermas-Genoese transformation, if we can find some tiny Walser symmetry such that the component 1 map to component 2 or transform to component 2, there's some symmetry. And for this particular model, if we do this transformation, so the tiny Walser map a component 1 to component 2, there's a sign depends on whether it's A sublattice or B sublattice. Okay, the sign for A sublattice is positive, for B sublattice is negative, and then you see that this non-interacting part, this part from Habermas-Genoese transformation, they are invariant under this Habermas-Genoese transformation. Under this tiny Walser transformation. Okay. So this Boltzmann weight is positive definite because of the tiny Walser symmetry between these two components. Okay. In terms of the auxiliary field, this Spinach fermion model, the sign problem, people has thought that this model has sign problem for like 3 decades. But using this Majorana algorithm, actually, it's quite simple to solve the sign problem. Okay. So the message here is to find some Habermas-Genoese transformation in the Majorana basis, and then if some internal relation between the Majorana components, especially tiny Walser or some anti-unitary transformation, which can relate a component to another component, and then this Boltzmann weight can be positive definite.
You could do further interactions as well?
Yeah. Yeah, so for the next nearness label interaction, the sign need to be attractive. So here for nearness label, this is positive. It's sign problem free. If it's attractive, it's not sign problem free, actually.
For the near neighbor?
Yeah.
To be positive?
Yeah. This is opposite to our intuition.
Yeah.
Actually, the original motivation to study this model is actually my motivation to study this Spinach fermion model is to study the attractive side. Because for the attractive interaction, the system will go to some superconducting phase. And so actually from mean field calculation, that superconducting phase is a pale density wave. It's a Kekulé, this Pelny amplitude, the nearness level Pelny amplitude forms some Kekulé pattern, which breaks the translation symmetry. is a pale density wave. At the pale density wave transition, there's an emergent supersymmetry. That's actually our study is motivated by Ashwin's work with Taro and Donna.
But you can't do that.
Yeah, well, we didn't solve that problem. Yeah, that's really the beginning of proposing this Majorana algorithm. We thought that attractive side is sign problem free, but it's not.
Question.
Yes.
So if we decompose the interaction in a density channel for like negative V, is that a sign problem?
Yeah. Simon discussed yesterday. So normally, if you decompose this density interaction in the density channel, and then it's sign problematic.
So you're saying for negative V and
Yeah, for either positive or negative, it's sign problematic. Yeah, because when you decompose that in the density channel, you will get, so you can still use this algorithm. You will get a single determinant, right? Since this is spinless. So in the density channel, as you can see, this density is, in terms of Majorana, there's some coupling between 1 and 2. So you cannot separate 1 and 2. Even in terms of Majorana, it's sign problematic. And this model for this positive interaction, so the quantum phase diagram discussed also by Simon yesterday, the Dirac semi-model, this interaction over T, this is a CDW phase. Sorry, Dirac semi-model. There's some cross-level quantum criticality at some critical interaction. Okay, we see over T. Okay. And this is this Majorana representation to solve the sign problem for this particular model. Actually, this algorithm can be applied to any fermionic system, not only spinless fermion, spin-4 fermion, and even SUM fermions, as long as there's some internal relation, tiny Volsov relation between the Majorana component is satisfied. So I guess so the plan is to to discuss the symmetry classification of the Majorana fermions. So I just sketch a little bit what kind of symmetry is required to be sign problem free for such algorithm. So as I mentioned earlier, we want to find a symmetry of this Hamiltonian, which is obtained after the Hubbard-Stranovic transformation. Okay, so the gamma is a Majorana fermion, which has site indices and component 1, 2 also spin indices, depends on the problem we look at. Okay, we would like to know what kind of symmetry is required for such Hubbard-Stranovic Hamiltonian, so that the problem is sign problem free. So the way to classify the sign problem for such this fermion bilinear is to use the anti-unitary symmetries. So previously I mentioned there's some tiny Volsov symmetry because tiny Volsov involves a compressed conjugate. So we can use this kind of algorithm or this classification scheme. So we ask how many tiny Volsov or anti-unitary symmetry is respected by this H. Okay. For instance, and this Hamiltonian H respect n anti-unitary symmetries. Okay, and these anti-unitary symmetries, they all anti-commute with each other. Sorry, this probably not the so they all anti-commute. Okay. So for each anti-unitary symmetry, the square of this anti-unitary symmetry can be either +1 or -1. Okay. So this is this classification scheme we want to use. So and then we look at what's the minimum symmetry is required, such that this is sign problem free. When n equal to 0 means there is no anti-unitary symmetry for this H. Okay, and then we know. So there is no symmetry, and this is sign problematic. There are many examples. For instance, a positive U-Hubbard model away from half-union. You can always do Hubbard transformation and in this Majorana representation. And if there's no symmetry, I mean it's not proof, but at least in this algorithm, it's sign problematic. Okay. If n equal to 1, so we can have a single anti-unitary symmetry which is respected by this H. And there are two cases. The square of this symmetry is +1 or -1. Both of these actually are not good. They all problematic. There are many examples. If n equal to 2, one choice. If both of them square equal to +1, this is not good. If one of them square to -1, this is good. If all of them square to -1, this is also good. Okay. It turned out that the problem I just mentioned for this Spinach fermion on the honeycomb lattice at half-union, it is in this universality class, or in this symmetry class. Sorry. So you can identify a tiny Vossel or anti-unit symmetry which square to either +1 or -1. Actually, for this Hamiltonian, this H0 plus this part, actually you can identify two anti-unit symmetries which anti-commute with each other, which is in this in this symmetry class.
What about when B is positive? When it's attractive.
When it's attractive, we can only identify one anti-unitary symmetry.
You do the Hubbard dynamic always.
Yeah. So it really depends. Yeah. So after the Hubbard, maybe there's some clever way to find the correct Hubbard transformation, such that it's sign problem.
I see. But in terms of original degrees of freedom, is there like a mapping to original back degrees of freedom about these criteria?
No, so this classification really about this bilinear Hamiltonian. It's like the topological insulator. It's like, so this is like D3 class or something like that. Okay. Yeah, it's not about the interacting problem. Yeah, it's indirect. And this tells us that for a specific model, so we can try to do some try to look for Hubbard transformation to have this kind of property, two anti-unitary symmetry with this property.
So one in two anti-unitary symmetry.
Yes.
Part of using the Majorana basis.
all of them using the Majorana basis. Yeah. So in the Majorana basis, this anti-unity symmetry is again use this unitary part times the compressed conjugate, and this unitary part is orthogonal matrix. Okay. So if it's symmetric and orthogonal, and then this t square equal to +1. If we use anti-symmetric and orthogonal, t square equal to -1. Yes?
Can I think of the product of the two anti-unitary symmetries being a unitary?
Yeah, that's correct.
And then I make a block diagonal structure? Is that
No, lot.
now will give you the doubling you need?
Yeah, so for, yeah, that's correct. For this class, and then we can form a unitary symmetry, the product of this T1 and T2. And then you can block diagonalize. So in the Majorana basis, this is essentially block diagonalize. The component 1 is decoupled from component 2. Yeah, that's another way to say that. I mean, in general, if you have some Habermas general transformation, it's not obvious. I mean, this is decoupled. As long as there's some anti-unity symmetry identified, you don't need to prove it's decoupled between two blocks. Using this, you can prove it's a sign problem free.
What Habermas transformation field to use is not always, it's not unique.
It's not unique, yeah.
It's not always obvious.
Yeah. That's the part which is, which we don't know how to systematically solve. Yeah. So if n equal to 3, this if all of them are, if we are T plus, if we can find 3 anti-unity symmetry, but all of them is plus, which is actually not good. The positive real Habermas model away from half-union, we can find 3 anti-unity symmetry, all of them anti-commute with each other, but it's still there's a sign problem. But for all other cases, that's fine. It's sign problem free for n equal to 3. For n equal to 4 or bigger than or equal to 4, all of them are good, are sign problem free. Okay. So basically, the most fundamental symmetry class is these two. Okay. All right. And so this is mainly about the algorithm of Majorana Cornell Monte Carlo when it's sign problem free. We also use this sign problem free Cornell Monte Carlo to study a number of interesting models. And the first model we studied is this Spinach fermion model with CDW transition to study the quantum critical point, identify the quantum critical point and also the critical exponent at the transition. And in the remaining probably 5 minutes, so I will discuss, the plan is to discuss 3 quantum critical points. Okay, let me try. The first one is the H quantum critical point. And this I discussed a little bit yesterday using renormalization group analysis, the quantum critical point on the surface of a topological constraint. Ashburn as calculate also has a nice proposal of realizing supersymmetry on the boundary quantum critical point of a topological insulator or topological superconductors. Recently, we applied this Majorana algorithm to study quantum spin Hall insulator or 2D topological insulator with backward scattering. So imagine we have a quantum 2D topological insulator on the honeycomb lattice, okay, with interactions. And so we can have a model which is original Ken-Milli model, this non-interacting part with atomic spin-orbit coupling plus Hubbard U. Okay, and this part conserve total SZ. Okay, total SZ is conserved, yes. And if total SZ is conserved, there is no H backward scattering, two-particle backward scattering. So the system for this non-interacting part, it has helical H mode, right? So this H is a spin up, moving to the right, spin down, moving to the left. Because of total SZ conservation, even with Hubbard interaction, there is no two-particle backward scattering. However, two-particle backward scattering actually should exist in a generical system when the system has Rashba spin-orbit coupling. Rashba spin-orbit coupling can flip the spin from spin up to spin down and vice versa. Okay. In order to study the stability of the 2D interacting topological insulator with two-particle backward scattering, we need to consider a Rashba spin-orbit coupling. And here, it turns out that with Rashba spin-orbit coupling, the model is still sign problematic. But we consider Rashba interaction. Okay. Instead of single particle spin flip, we consider two particle spin flip. On a bond, two spin down can flip to spin up, and vice versa. So if we consider this two spin flip interaction, and which we call Rashba interaction, it turned out that this model, the whole model is sign problem free using the Majorana algorithm. Okay, and then we can study the quantum phase diagram of this model. Okay, suppose, yes.
You can go away from half billion with the Majorana basis?
No, still at half billion. So it's a.
That was sign problem free without using Majorana basis.
No, so without this term, and this Ken-Milli Hubbard is sign problem free. That was.
Can handle Rashba.
Yeah.
Still at half billion.
Yeah.
Can handle Rashba.
Yeah. That's the part. So for this non-interacting part, there's a hopping T we set equal to 1. There's some Ken-Milli atomic spin-orbit coupling we can set to some parameter 0.3. And this model describes a topological insulator. So now we can study the quantum phase diagram of this model with open boundary condition, with H. Okay, a system with H. It turned out this is the quantum phase diagram we obtained. So this is a 2D TI. So when the interaction is weak, even with the two-particle backward scattering, the 2D TI is still stable. Okay, and this region has H symmetry breaking, tiny universal symmetry breaking. And this, when the interaction is too strong, the 2D multi-insulator. Yes. Yes, right. Antiferromagnetic multi-insulator. Yeah. Actually, the H will form some ferromagnetic state. Okay, which break tiny universal symmetry, which gap out the helical mode. But as long as this interaction U is not sufficiently strong, and turning on this two-particle backward scattering won't destroy the helical edge state. It's still robust. Okay. So this is the model we studied recently. Another model is this 2D interacting topological superconductor. this, so we can consider consider a topological superconductor with a p plus ip pair for spin up electrons, but p minus ip pair for spin down electrons. So which respect tiny Waltz symmetry, and then we can add some interaction to see how robust the edge state is. And this is motivated by, so this is the non-interactive part. So this is motivated by Ashwin and Tyrone and Donna's work of realizing supersymmetry. Okay, they propose that this model, when this model have edge quantum critical point, the quantum criticality only on the edge, emergent SUSY occur at that quantum critical point. So again, we can study the phase diagram of this. So they said this is the p wave, the strength of the p wave pairing. This is the interaction. So this is what we get.
What is H naught?
H naught describes this p plus ip pairing for spin up electrons and p minus ip pairing for spin down electrons. Yeah, this is the BDG Hamiltonian. Yeah, sorry. And hopping is T. There's some chemical potential on the square lattice, for instance. This is away from hopping. Okay, the chemical potential is finite. For instance, there is a parameter characterizes the p wave pairing, the p plus ip pairing. And again, so there is the H quantum critical point, and there is a bulk quantum critical point. So this is a 2D TSC. Again, this is a H tiny Waltz symmetry break. So this side is a trivial superconductor. Okay, the bulk break tiny Waltz symmetry. On this region, only H break tiny Waltz symmetry. The bulk is still tiny Waltz invariant. Okay, and this part, both H and bulk are tiny Waltz invariant. So there's when we move the interaction along this direction, there's a H quantum critical point along this line. And Ashwin and collaborators, they predict that at this H quantum critical point, there's the n equal to 1 SUSY, emergent SUSY. And they, yes?
Usually you have just one quantity to determine superconductivity, like the pairing operator.
Yes.
How do you differentiate the 2D topological superconductor from the trivial superconductor, just looking for the pairing operator?
No, here, so we for the non-interacting part, we know there's a helical Majorana mode. Okay, and this helical Majorana mode is robust against some weak interaction. As long as there is no symmetry breaking and the phase doesn't change on this side, it's still topological. On this line, when it's non-interacting, it's topological superconductor, right? Yeah, it's from the adiabatic continuum. And so we calculate this critical exponent and also the mass of fermions and bosons. Found that the mass of boson and fermions they are equal to each other or close to quantum critical point, the H quantum critical point, which verify their prediction of n equal to 1 SUSY. Yes?
So I have a question then,
Yes.
technical. So you do quantum Monte Carlo on a system with open bound?
Yes,
here,
yes.
And your system
On a
is
cylinder.
gapless, right?
I'm sorry?
Your system is gapless because of this.
Yeah.
So how do you do that? Like because you want to do like 0 temperature.
Yeah.
And then your system is gapless.
Yeah. So that's fine.
Oh, that's why?
Yeah. So here, sorry, all the phase diagram I drew here zero temperature quantum phase diagram. And so for quantum Monte Carlo, there's an algorithm called projector algorithm, which really studies the ground state property of the system. Instead of, I didn't mention, instead of study the trace of e to the minus beta h, for the projector quantum Monte Carlo, you choose some trial wave function, and then use this projection operate. Here, beta is not a temperature; it's just some projection parameter. Okay, when beta is sufficiently large, the system will be projected to the true ground state. Right. In numerical simulation, we choose some large beta and then see whether the result changes when we use even larger beta to see whether the result converges or not. Yeah, normally we choose beta equal to 100 times 1 over t. T is a hopping. And then we can use 150 to see whether the result changes or not, converges or not. It's not really infinity. It's
I mean, it's still an exact unbiased method, so
Yeah.
trial wave function sounds like, but as long as that initial wave function has some overlap.
yeah. All right. So this is this interactive topological superconductor model we studied to identify the predicted age supersymmetry.
So the trivial superconductor, did you break the symmetry there? Or
Yeah. 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 So this so here is attractive U. Attractive U forms some S wave, but the S wave has a relative phase pi over 2. It's IS actually. So it's a P plus IP, P minus IP plus IS pairing. It's like D plus IS pairing. This rectangle also symmetry. Una, how much time do you want to give?
You have, let's say, out of 3, you covered 1?
Yeah. I think I can stop anytime. So this is, yeah.
2 minutes?
Yeah, okay. So,
1 per.
so the second quantum critical point I would like to briefly mention, is the fermion-induced quantum critical point. So we propose a model which has a quantum phase transition between direct semimetal and Kakulli valence bond. Okay. Kakulli valence bond is a phase. The hopping breaks the translation symmetry of the lattice. Okay. And this symmetry breaking is Z3 symmetry breaking. Okay, it breaks this C3 rotational symmetry. So normally, this kind of Z3 symmetry breaking is a first order phase transition. Okay, because if we write down some Ginsburg non free energy, the cubic term of the order parameter is allowed in the free energy, in the effective action. Okay, non-law tells us that this transition is first order. However, we are really studying a fermionic quantum phase transition. Fermion play a role to determine the nature of the quantum phase transition. So it turned out that depends on the number of flavors in this problem. When n equal to 0, this Kakulli transition certainly is first order. Namely, in some bosonics, in some insulator, if there's a Kakulli transition, it's a first order phase transition because of the cubic term in the Ginsburg non-free energy. But when n, from our quantum Monte Carlo simulation, the sign probability simulation of the model, I don't have time to write down the model, we found that we calculate n equal to 2 all the way to 6. We always found continuous phase transition instead of first order phase transition. Okay, and this is second order. Okay, and this is from the quantum Monte Carlo result. Okay, and then we do realization group analysis showing that when n is bigger than some critical value, and this quantum phase transition is driven to be a second order phase transition. Second order. So it's called fermion induced quantum critical point. So when n is less than some critical value is a first order. And the value of this critical flavor is not known yet. And from numerical result, we think that it's less than 2. Moreover, when n is equal to 1/2, namely we have a Majorana fermion at each site, at this, if this transition is continuous, that quantum critical point will have emergent supersymmetry. From that, we can derive the scaling dimension of the cubic term. The scaling dimension of the cubic term is 2, which is less than d equal to this 2 plus 1, 3. So the cubic term is relevant for n equal to 1/2 from the exact supersymmetry. So the critical value nc we conclude is bigger than 1/2 but less than 2. Okay, so this is exact. The lower bound is exact from the super. Not exact. I mean, this value is we know, but this upper bound is from the quantum Monte Carlo simulation. Okay.
So you put the n equal to 1. That's my problem.
Yeah, that's a good question. We are trying to find a model which is sign problem free and which can induce this calculate pattern. The model we constructed for n equal to 1 actually is this CDW model. So we get into some CDW phase instead of calculate pattern. But for n bigger than 1, from 2 all the way to 6, so we get calculate transition from the semi-metal to calculate, and the transitions.
How much does it enlarge the unit cell?
This just triple the unit cell. Yeah. It's a Z3 transition. Yeah. Yeah. Thanks a lot. Sorry.